This is problem number 4 for the Exam 1 review. The non-ideal characteristics for an op-amp are going to be considered in this problem. It's given that the input offset voltage, which is labeled as VIOS, is 2 millivolts. The unity gain bandwidth is F of t is 100 megahertz, and the slew rate, meaning how fast the output can respond to the input, is 4 volts per microsecond. So the first step is to find the overall gain of the circuit. The input is coming in at the positive terminal, so therefore a non-inverting amplifier. So 150K over 10K plus 1, which gives 16 volts per volt. So the gain is 16 volts per volt. So looking at the bandwidth, there's going to be two limiting factors. There's going to be the factor from F of t, the unity gain bandwidth, where the bandwidth is determined. This point where it intersects the dB axis at 0 dB is 1 volt per volt, therefore unity gain 1. This is the value that's given on data sheets. What we want to know is this point, which is the F3 dB, which is going to tell us the actual frequency range of the circuit. This is the gain, and then it starts to drop off after the frequency at the 3 dB point. So these are related by F of t, gain times F3 dB. In this case, F of t is given as 100 megahertz. The gain we just determined as 16 volts per volt, and we can solve this for the 3 dB point then. F3 dB for this is going to then be as 6.25 megahertz. From the slew rate, which also has a frequency effect, the slew rate has the limitation where the frequency maximum is the slew rate divided by 2 times the peak value at the output times pi. So this is the peak output value. So for this circuit, it was stated in the problem that the supply was a plus and minus 12 volts, and that the circuit has an output swing limit within 2 volts. So again, that's a typical thing that you'll see on the data sheet, is that the output swing limit is within 2 volts, meaning that the max out would be an amplitude of 10 volts. So in this case, we're going to put 10 in here. For the slew rate, it's 4 volts divided by microseconds. This is the most common mistake I see, is that the microseconds is forgotten here. So a minus 6 for the microseconds, 2 pi 10. So for this, the frequency limitation is going to be a maximum of 64 kilohertz. So these are very different from each other, and dependent on the gain of your circuit, the F of t can become the limiting factor instead of the slew rate. For this one, where our gain is 16 volts, we have the 3 dB point is 6.25 megahertz. So this circuit is said to operate up to 64 kilohertz. All right, the other thing that is wanted to be known is the peak value at the output considering the input offset voltage. So the peak value, if we're given the input, which we would need to know here, the input is given as 0.1 sine omega t, assuming that the omega is less than the 64 kilohertz. And to find this then, we know our gain is 16. So we can take 16 times this. And we get 16 milli sine omega t plus we now have the offset voltage. So the offset voltage is determined by the gain times the offset voltage itself. So 16 times 2 milli, so we have another additional 32 millivolts. So looking at a graph, which we assume is going to be centered around 0 on the sinusoid out, ends up not being around 0. It has a DC shift of 32 millivolts, approximately. Again, this is not a fixed quantity and it can vary. And then the sinusoid will be around the 32 millivolts. So our peak value, which is what we want to know here, is going to be the combination of the peak of this plus the 32. So it's 16 milli plus 32 milli for a value of 48 millivolts. The last question is asking how this circuit can be modified to compensate for the input bias current. Now the input bias current we assume in the ideal case that the current going in is 0. What happens with the input bias current is that it is not 0. It is a small value. Because of that small value, I now have another additional voltage that's seen here in addition to my input source, which can then also be amplified and give me an offset at the output. So to compensate for that, what I want to do is take the resistance to be the same at each input node. Therefore, the input bias currents will be approximately the same. That I times R will be a common value on each one and therefore cancel out. So in order to make the resistance that's seen at this node the same as the resistance seen at this node, I'm going to put in a resistor, and it's going to have the value that this impedance sees, assuming that the output is 0 and the input is 0. So that would mean it's 10K in parallel with 150K. Again, that's 10K in parallel with 150K. And that will compensate for the input bias effect.